Hello, I'm Hunter, and welcome to Hayden and My Controls video. In this video, we will be showing the application of control theory with regard to motorcycle balance. The specific case we will be inspecting is the motorcycle's behavior when riding on its rear wheel alone. The first step in designing our control law is defining the system. Steady state for a motorcycle involves having both wheels in contact with the road surface, but we're interested in what an excited state would look like and how to control that. More specifically, the case of the wheelie. This is performed by applying a large torque to the rear wheel which drives the bike forward. The front of the bike has a tendency to rise into the air as a result of the moment, which is a result of the perpendicular distance between the high center of gravity and the applied torque, or actually, the friction resulting from the applied torque. This creates a situation where, balanced on one wheel, the motorcycle acts as an inverted pendulum, and the behavior can be described in much the same way. This system would benefit from a properly designed control law because if the large amount of acceleration is applied improperly, catastrophic results may occur. This system, being a motorcycle riding on one wheel, could be considered a continuous system, as the system state can be defined to infinitesimal size at any point in the allowable range. Inputs to the system would be the application of the throttle, which is directly transformed into wheel torque by the engine cycle. Outputs for this system would include pitch angle and pitch rate. Quantities measured would also be pitch angle and rate and wheel torque. A negative feedback loop would be necessary to correct for error, as positive feedback would merely excite the system beyond the desired state. The photo on the left, courtesy of strangevehicles.com, is an example of the behavior we hope to avoid, and is a result of too much overshoot. Pictured on the right are the governing equations of an inverted pendulum, where the x dot, and x double dot refer to the rear wheel position, velocity, and acceleration, and phi dot, and phi double dot refer to the pitch angle, rate, and angular acceleration of the system. In designing a control law, it is important to note that this system is not inherently stable, but it can be modeled as a linear system via Lyapunov's stability theorems, and an equilibrium point can be found, or chosen, based on the torque applied. For control of this system, we would need to apply a PID controller with a negative feedback loop, which would have to be tuned for each scenario. But our desired performance metrics would be to have a minimal overshoot, almost zero, and a very fast rise time of under a second and a reasonably fast settling time, less than 2. Pictured here is the simulating block diagram which could be used to model the system. Shown is the command torque applied as a step function, the PID controller which would need to be tuned for various torques, and the transfer function of the equations pictured earlier. Reference frames involved in this system are the ground or inertial frame, the body or fixed frame attached to the bike, and the wheel frame attached to the wheel.